Welcome to Lesson 2A, Concentrations. We're going to discuss various ways to describe concentration of a species of gas. We're assuming a gas mixture. Notice that we'll always assume ideal gas mixtures, and we'll show how to convert between these various concentrations and also discuss how to calculate the mass flow rate of a species. Not just the bulk flow rate, but the mass flow rate of the species in a gas mixture. We already defined mole fraction previously, so we have this Yj as Nj over Nt. It's unitless. Typical dimensions are parts per million or parts per billion, and the dimensions of Nj are 1. In other words, it's dimensionless. Also unitless, but we've kind of invented these parts per million and parts per billion as a pseudo unit. And then we had this very important equation with lots of stars to convert between mole fraction and partial pressures and partial volumes related to total pressure and total volumes. So now let's define mass concentration. This is kind of like a density, mass over volume, except it's the mass of species J per unit volume, not the total mass like you're used to. Like density of air in a tank would be the whole air, everything in the tank divided by the volume. This is just of species J. So the dimensions of Cj are the same as density, mass over volume, or in terms of primary units, mass over L cubed, because L cubed is volume. And the typical units are shown here: milligram per meter cube, microgram per foot cube, microgram per liter. There's all kind of different units you can think of. A milligram per meter cubed is probably the most popular. And then we can similarly define a molar concentration similar to mass concentration, except it's number of moles per unit volume instead of mass per unit volume. So it's moles per meter cubed, moles per foot cubed, moles per liter, etc. And the dimensions of C molar J would simply be number of moles per volume, like that. Now, sometimes we use molar concentration. A lot of the time we need mass concentration, but suppose you're given mole fraction and you want to calculate mass concentration, etc., vice versa. You have to be able to convert between all these different types of concentrations. We're always talking about ideal gas mixtures. Let's do a bunch of different conversions here. So the first one will be between C molar J and Cj. These are lowercase c's, so in other words, molar concentration and mass concentration. So how do we do that? Well, this one's pretty easy because we know that by definition, Mj is Nj times capital Mj, and from that we get Nj is little mj over capital Mj, and we know our molar concentration C molar J is defined as Nj over V. We have that right up here. So I'll just plug in this Nj into there. And so I get Mj over capital MJV. And now let's recognize Mj over V is equal to Cj. So this tells us then that C molar comma J is equal to Cj over Mj. So that's nice and simple, and the only difference between mass concentration and molar concentration is molecular weight. That makes sense because molecular weight is defined as mass per mole. You can sort of do it in your head anyway. All right, let's do one a little more complicated, but still not real difficult. But let's do a conversion between Yj, mole fraction, and Cj, mass concentration. I'm going to start with mass concentration definition. Cj is Mj over V. That's from up here. And then remember, we have ideal gases we're talking about, and we also have these, this one will be useful to us, Yj is Pj over P. So I'm going to start with Cj is Mj over V. Then the ideal gas, we had Pjv, and this is in terms of partial pressures. Remember, there's different ways to write ideal gas equation. If we write it in terms of partial pressure, we have Pjv equal Nj_RUT. And now use this Nj, similar to what we just did. Nj is little mj over capital Mj. And from that, we can solve for the volume so that we could stick it in this C equation, divide through by Pj also. So this is Mj RUT over capital Mj Pj. Plug that into Cj, and we get this expression, but notice that MJ's cancel. And now we're going to use what I told you to remember from the previous page, and that is Yj is equal to pj over p. That was that equation that we put lots of stars around the other time. And so from that, pj is p times yj, and let's stick that into here. So finally, we get cj is yj, capital MJ, p over RUT. There's a few equations in this course that I call workhorse equations, and that means we use them all the time. So this is one of these workhorse equations. It's actually just a conversion, but there's many times when we'll be doing a problem and we have, say, mole fraction Y and we need mass concentration or vice versa. This is how you convert between the two. Now I want to make a couple comments here. The first one is that since Yj by definition is Nj over Nt, it is independent of pressure and temperature and volume. And so what I mean is if you have say you have a tank, this is our gas mixture in here. And so this is state 1, and we compress it like that about a factor of 2. So this is state 2. We have a certain Nj and we have a certain Nt. We have Nj and we have the total number of moles and the number of species J moles. And assuming there's no leaks, we haven't lost any of those. So we still have the same Nj and the same Nt. So Yj is independent of pressure, temperature, volume. We can pressurize this tank, heat it up, whatever we want to do. As long as we don't have a chemical reaction, and we don't have any leaks, we're not changing Yj. So how about Cj? Well, Cj is Mj over V, and this depends on volume. If we take the same two states, so we have a tank, so this is just kind of a thought experiment. So we have our Nj in there and we have a certain volume, let's call this 1, and now we compress it. So we have a volume 2. If there's no leaks, we haven't lost any Nj, so we have the same Mj, the same Nj, but we have a different volume. So it definitely depends on V. The concentration, the mass concentration in tank 2 in this second case, rather the second state, will be greater because you have the same Mj, haven't lost anything, but you have a smaller volume, so Cj would get bigger. So it does depend on volume. Similarly, C molar J, and that's just Nj over V. And you can make exactly the same argument as we did above. So this also depends on volume. Now, some books will say that mass concentration depends on pressure and temperature, but that's not precisely true. Now let me ask a question here. I'll state it as a question like I would normally do in class. Question is, in a closed container, does Cj change if P and or T change? In other words, is Cj dependent on temperature and pressure?
Yes, I think so. I think it depends on how P and T change. I have no idea, dude.
The answer is not necessarily. And I will again use the same kind of logic here. So let's look at case 1, where we have some tank piston arrangement, and here's case 1, and all we do is compress it for state 2. And so here we know that P has gone up and V has gone down, and temperature has gone up unless you have some heat transfer going on. And the only thing that matters is the volume, because Cj is defined as Mj over V. So we haven't lost any mass. There's whatever Mj is here is the same Mj here. So Cj does change. So we'd say, yeah, it's dependent on pressure and temperature because these pressure and temperature changed. And so it does change with pressure and temperature, but it's really changing because of volume. Let's think of a different thought experiment. Case 2, now we have a rigid tank. So here's V1 and here's V2, and V1 is equal to V2. And let's suppose we add heat here. So in state 2, we have a different T2, say, is greater than T1, and P2 is also not equal to P1. We can change the pressure and temperature in that tank, but as long as the volumes remain the same, then Cj1 equal Cj2. So in this case, it's not directly dependent on pressure and temperature. So it's dependent on volume, but sometimes the temperature and pressure can change such that the volume stays the same as in this case too. So you really can't say that it depends on pressure and temperature. So here's how I will state it more precisely. I'll state it that Cj and by extension C molar J are not directly dependent on pressure and temperature. They are dependent in the sense that if pressure and temperature act enough to change the volume, then they will be dependent. So that's an interesting sideline. Now, I want to talk about mass flow rate of species J. We already talked about bulk mass flow rate, and so we're talking about flow through some kind of a duct. So here's a duct, and we have some bulk mass flow rate m dot, or a bulk volume flow rate q. You should recall then for the bulk, m dot is rho q, and this is the bulk mass flow rate through the duct, or the total mass flow rate through the duct. That includes all species. Typically, again, it's air plus one or more contaminants or air pollutants. So now let's define m dot j is the mass flow rate of species J. So pick one of these contaminants, or it could be the air, but typically we're talking about species J, the mass flow rate of species J only. And so we'll define m dot j as mj, mass of J over time, which is mass of J over volume times volume over time. Just multiply and divide by volume. And so this gives me mass per volume is Cj, and volume per time is Q. So we have a nice simple equation then, m dot j is equal to Cj times Q. So if you know the bulk flow rate and the mass concentration, Cj, you can easily calculate m dot j. And I have a caution here I'll put in red, is that this Q that we're talking about here must be the actual. Remember, we talked about the difference between actual Q and standard Q. So this has to be the actual Q, not the standard Q, because we're multiplying and dividing by the same volume there. And so you would get messed up if you did it the other way. So make sure when you're using this formula that you use actual volume flow rate, not standard volume flow rate. Let's do an example. We're given that air with ammonia vapors, so it's a gas mixture, flows through a duct and then out into the atmosphere. And we're given these properties here. The bulk volume flow rate is given 1,000 actual cubic feet per minute. We're given the mole fraction, 5 parts per million of ammonia vapor. We're given its molecular weight, I looked it up already, the temperature and the pressure. We want to calculate a few things here. So the first thing I want to calculate is the bulk volume flow rate in standard cubic feet per minute. And so for that, I'm going to use this equation we had from a previous lecture. Q standard is Q actual, P over P SATP, T SATP over T. So I plugged in all the variables and the units. If you write it this way, the units cancel out nicely. The KPAs cancel and the Ks cancel. We have feet cubed per minute, so this is standard cubic feet per minute is our answer, 560. Next, we want to calculate the ammonia mass concentration. So I wrote that conversion equation that I told you was our workhorse equation. So let's plug in the numbers there also. So I plugged in all the numbers and units. You got to be very careful with units. I don't know how to stress that anymore. Notice I had the molecular weight of ammonia was 17.0 gram per mole, but I put it as kilogram per kilomole. That's always fine to do as long as you keep both top and bottom the same, either gram per mole or kilogram per kilomole. And then these are all unit conversions that you should be familiar with. Kilojoule is a kilonewton meter, kilonewton per meter squared is a kPa, because a newton per meter squared is a Pascal. And then of course 10 to the 6 milligram per kilogram, and I wanted my answer in milligram per meter cubed. And so to 3 significant digits, I would write my answer as 1.94 milligram per meter cubed. Comment, we are only given 2 significant digits up here in the concentration, in the mole fraction. But in general, unless I tell you differently, always give your answers to 3 significant digits. All right, finally, let's calculate the emission rate into the atmosphere in units of grams per hour. So here's my equation, m dot j is CJQ, and I put in red here, this again has to be the actual Q, not the standard Q. So make sure you use the proper flow rate. So this becomes m dot j equals 1.9447 milligram per meter cubed. Notice I'm using a lot of extra digits here just so I don't have round off error, times the given 1000 ACFM, actual CFM. And then the rest is all going to be unit conversions. 0.3048 meters per foot cubed, and then 60 minutes per hour. Gram is 1,000 milligrams, and we get our final result, which is 3.30 grams per hour. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.